So I'm going to present the project that my team made being stimulated by this challenge. So we were thinking how can we contribute to this growing open source and open data movement, and we decided to create a package that would help people with little or no programming experience to start analyzing their data in a novel way. And this way is trying to predict post-stimulus reaction based on pre-stimulus EEG signal. So I would talk a little bit about variability within post-stimulus response and how it can be accounted by pre-stimulus brain state. And with a few examples, I hope to convince you that this is a very promising line of research. And then I will describe the package that we made and draw some conclusions. So the types of post-stimulus response that can be used in these paradigms are very different. So it can be simple behavioral things such as reaction time or performance, like does a person perform the task well? And it can be neuroimaging data, for example, event-related potential component latency and amplitude. It can be motor-evoked potential in transcranial magnetic stimulation paradigms, and actually it can be any other measurement you can come up with. And what is similar in all these measurements is a very high degree of variability, especially with EEG signal. You can look at different EEG segments, and the ones that are marked with X are periods of time following the same stimuli. And you can see how dramatically they are different. And it is very hard to work with this kind of signal. So people usually average out all these dramatic variation because it is assumed that well, everything else is noise and it will simply cancel out. But maybe we are losing some important information, and so an alternative to simple averaging would be trying to explain the variability. And it can be done by looking at what is happening right before the stimulus is presented. And we need to try to analyze brain states. And we all intuitively understand that we are continuously changing from one brain state to another. We can feel drowsy, or we can be fully awake, or we can pay attention or be distracted. And these can be characterized by different oscillatory patterns. So on the screen to the right, you can see different oscillatory patterns. They are mostly characterized by their frequency. And looking at the signal, we can check what is the dominant frequency band, and we can look at phase synchronicity across different location, amplitude of particular oscillation, or variability of a frequency band. And also we can look at how different frequency bands are correlated with each other. And all of this has been shown to correlate with different kinds of activity and different types of brain state. And so here are a few research examples that show that this is this can help explain the variability. So in this study, it was shown that performance in a psychophysical task, which was detecting near threshold stimuli, was predicted by amplitude of alpha oscillation as well as beta and gamma. And what was interesting is that in one brain area, parietal area, the relationship was linear. So the higher the amplitude, the better is performance, the smaller is reaction time. But for sensory motor region, the relationship was similarly parabolic, or like definitely non-linear. So only medium amplitudes were optimal for better performance. Another study examined N100 amplitude, which is ERP component, the most general one that is observed as a reaction to, well, most often auditory stimuli. And it was shown that phase synchronicity, so how synchronized are different parts of the brain, predicted higher N100 amplitude. And such research can help explain the huge variability in EEG signal that we observe. Yet another study comes from transcranial magnetic stimulation paradigm, which is a very interesting field, and it was observed that with the same transcranial magnetic stimulation, which can induce some motor movements, we observe very high variability, so in amplitudes of motor evoked potentials. And interestingly enough, the power of oscillations themselves did not predict this variability of motor evoked potential, but the variability within high alpha power was correlated with motor evoked potential's amplitude variability. So you can see that there are very different studies that are linking different post-stimulus reaction to very different pre-stimulus characteristics. And this motivated us to create an open source package, especially because now we see a dramatic improvement in quality of EEG recordings. Now when the signal to noise ratio is lower, we cannot just average things out and say that, well, everything else was just noise. And with better spatial resolution, we can look at signals more precisely, like which part of the scalp contributes more to the signal. And especially now when we can observe single trial ERP, we can really look and nail down the predicting factors for variability in event-related potentials. And with a lot of open data, this line of research can be applied to many different paradigms, many different studies, because you don't really need to change anything in the studies. You already have all the necessary data, and you can repurpose it in very creative ways. And now we have a lot of tools to analyze data from different modalities, but there was no tool for integration, and so this is why we created this open source package, which is an interactive MATLAB toolbox, hopefully user-friendly graphic user interface. So user can input a variety of data, and it allows a user to view EEG data, to compute and view spectra, and also compute power for chosen frequency band, a variance within this frequency band, also to compute ERP, and eventually to sum it with Spearman correlation between pre-stimulus and post-stimulus data. And it can also plot resulting correlations on an electrode map, which really helps to visualize which part of the scalp contributed more. So here is the viewing tool. This is the viewing spectra. So here you can see nicely which is the dominant frequency in the data, like looking at this bump. And we tested this package with data from Iskan et al. And here you can see how the correlations can be plotted on the scalp. And not only correlations, but also p-values. So you can see that only frontal part, for example, showed. This is for oscillation power, and this is for standard deviation over the scalp. So we hope that our open source package can help neuroscientists to join this line of research, and this will hopefully contribute to our understanding of neural bases underlying different cognitive processes. And in terms of variability of post-stimulus responses, we can maybe categorize different responses into subgroups, and it can help our analysis. And it can also contribute to our understanding of individual differences that we observe. So thank you for your attention.
Panasonic.